In this video, we're going to look at National 5 chemistry calculations, specifically looking at balancing chemical equations. So a good place to start would be this worked example here. If we're going to balance this chemical equation, we can see the first thing we've done is we've looked at all the atoms that are present on the left-hand side, and we've written down the symbol for them. So we've got carbons, we've got 2 of them, so we've got a C down the middle, in line with this arrow, 2 on the left and 1 on the right. We've got 5 plus 1, 6 hydrogens on the left, and we've got 2 hydrogens on the right. And then finally, we've got 3 oxygens on the left, 2 within the diatomic oxygen, and 1 within this molecule here. And then on the right, we've also got 3. So a good place to start would be with the carbons. So it looks like we need to have twice as many carbons on the right-hand side for this to work out. So an easy way to do that is just to put a 2 in front of the CO2. When we do that, if we appraise what our numbers look like now, the carbons are now fully balanced, the hydrogens are still out of whack with 6 on the left and 2 on the right, and the oxygens, which were actually completely fine, are now imbalanced. So I would say we could now either fix the hydrogens or the oxygens. Because you've got this lovely oxygen on its own here, diatomic oxygen, if we balance the hydrogens and the oxygens are still not quite fixed, that's okay. We can put whatever balancing number we need to in front of that oxygen. So I think the first thing we're going to do is have a look at these hydrogens. We need to have 3 times as many hydrogens on the right-hand side. Now, if the hydrogens were split between more than one different molecule, that would be a bit tricky, but here they're all stuck within the water. So if we shove a wee 3 in front of that water, let's find out what happens. When we do that, the carbons haven't been affected. The hydrogens are now 66, and the oxygens are now 3 on the left and 7 on the right. Now, we've already done our balancing numbers for both the molecules on the right, and as I said, we've got this oxygen here, and it can sort whatever problems we now have. Now, the oxygen isn't only found within this, so whatever number we bring the oxygen here up to, we're then going to have to add 1 on from this C2H5OH molecule here. So if we think about, we'll try and balance this to 1 less than we need, and then we can add this extra 1 in. So we're trying to get it up to 7. So what number is 1 less than 7? That would be 6. So we're trying to get the oxygens up to 6, and then we'll add this extra oxygen on, and it'll bring us up to 7. So I reckon that if you bring this up to 6 by putting a 3 in front of it, we would have 6 plus 1 is 7, and then the oxygens would be balanced. So that would give us 5 plus 1 is 6, so that's not correct, is it? I think a previous teacher, we'll blame a previous teacher, has put the wrong balancing number in there. So there we go. So 3 oxygens on the left, so 6 plus 1 is 7. Yeah, so that makes much more sense. If we look at some of these practice examples, so in this case here, we put our atoms down the middle. So in terms of the carbons, the hydrogens, and the oxygens, let's see what we've got. So how many carbons have we got on the left to start off with? So we've got 9 carbons on the left, and we've only got 1 carbon on the right. So I'm going to go out on a limb, even just at this early stage, and say we're probably going to be putting a 9 in front of that carbon. On the left-hand side here, we seem to have 19 plus 1, 20 hydrogens there. And on the right-hand side, we only have 2. And again, I reckon that it seems sensible to maybe put a 10 in front of that, and that will multiply this out. And then oxygen-wise, we have 1 plus 2 is 3. And then on the right-hand side, we seem to already have 3. So my suggestion was, sorry, that was a 1. Getting ahead of myself here. I think if we put a 9 in front of this carbon, it will bring the carbons up to 9. What it's also done is it's affected the number of oxygens we have here. So 9 times 2 is 18, plus 1 is 19. So we have 19 oxygens now. So that's no good. We need to now somehow find a way to sort the hydrogens. So as I said, if we multiply this by 10, what we will end up with is 20 hydrogens. Now, let's take a full account from the start of how many oxygens we just have, because the carbons are fine, the hydrogens are fine, the oxygens, we've got 18, and then we've got another 10 here, so we've got 28 oxygens on the right-hand side. And on the left, we've got this extra 1 here, and then we've got 2 here, so we've got 3 oxygens. I would say whatever we're going to do to balance, I probably wouldn't be putting anything in front of this molecule here because that will change the carbons and hydrogens. And we've just spent a long time on the right-hand side sorting those out. So I'd say whatever we do to this, we probably want to undershoot 28 by 1. Because after we've balanced these oxygens out to 27, this extra one will bring us up to 28. So we would get our calculator app out, and we would try and find out what you need to multiply 2 by to get to 27. So 27 divided by 2 . (27) divided by 2 is 13.5. So if we put 13.5 in front of this oxygen, it will multiply by 2 because the oxygen is diatomic. So we'll end up with 27 plus the 1 from this oxygen brings us up to 28. Now that is an especially difficult question. Hopefully they're going to get a little bit easier from there. So similar within the balancing equations, the reason we're doing this is because the number of atoms on the left have to be the same as the number of atoms on the right for a given element. So it's similar to this question here. So we've got 2 hydrogens on the left, 2 hydrogens on the right. So you could do the same kind of thing where you write the atoms down the front. We've got 1 sulfur on the left, and we've got 1 sulfur on the right. We've got 4 oxygens on the left, and even just within this copper sulfate, we've got 4 oxygens. So X will have to have brought to the party an extra 1, 2, 3 oxygen. So let's just keep a wee track of that down here. So it looks like 3 oxygens are going to be coming from X. What else did X bring in? X seems to have brought copper as well. So we've got copper. And let's see, the hydrogens were from here. The sulfurs were from there. The oxygens are from there. So we're also going to have a carbon, and that should be it. So we've got a copper and we've got 3 carbons. Now, you're probably thinking if it's a metal ion and then we've got our 3 carbons here, that's going to be a group ion of some kind. If you go to your data booklet and you look for something that has in the group ion section a copper, something for copper to bind onto that's got a carbon and 3 oxygens, you can then come out with carbonate. So you're probably going to find is that this X here is copper carbonate. And then obviously with the 3, we'll have to make sure that is subscript. So copper carbonate. A reasonably tricky question, but actually still fairly doable. How many moles of oxygen would be needed to react completely with 4 moles of magnesium? So if 2 moles of magnesium needs 1 mole of oxygen, so here, how many moles of oxygen would be needed to react completely with 4 moles of magnesium? So this question is saying that with 2 moles of magnesium, you need 1 mole of diatomic oxygen to give the 2 moles of magnesium oxide. So here we're saying that 2 moles of oxygen would be needed if we have 4 moles of magnesium. This one's a little bit tricky because you might be thinking, well, a mole of diatomic oxygen contains 2 oxygens, but we are still saying for this balancing equation, we're talking about the number in front. So how many moles you would need? 2 moles. Balance the equation below. So H2O2, so hydrogen peroxide, will give us H2O plus O2. So there's 2 hydrogens on the left, 2 hydrogens on the right, 2 oxygens on the left, and 3 oxygens on the right. So to balance this off, what we can do is just put a half in front here. So that will give us half of this, so 1 oxygen plus this. So in reality, if you take 1 mole of hydrogen peroxide, you will get 1 mole of water and a half a mole of diatomic oxygen. Balance the following equation. So WF6 H2O WO3 HF. So how many moles of the W do we have on the left? 1. How many moles on the right? We have 1. How many moles of F do we have on the left? 6. And on the right, we have 1. That probably suggests we can put a 6 in here because now the fluorines balance. In terms of the hydrogens, we've got 2 on the left. We now have 6 on the right. So if we put a 3 here, that'll balance out the hydrogens. Again, you should do it by doing the nice column method, balancing it out. This is just speeding up a bit. So we've got the tungstens balanced, we've got the fluorines balanced, we've got the hydrogens balanced, and you've got 3 oxygens here, and you've got 3 oxygens there. So that all balances as well. Balance this equation. So we've got 5 carbons on the left, got 1 on the right, so we'll put 5 in there. So the carbons are now balanced. We've got 12 hydrogens on the left. We're leaving the oxygen to last because it's on its own, so we can put whatever balancing number we need in front of that to make it work. So 12 hydrogens on the left, and so that means we can put 6 here, and that will give us 12 hydrogens on the right. We'll then look at what a mess we've made of the oxygens. So we've got 10 oxygens here, and we've got 6 oxygens there, so that gives us 16. So if I chuck a cheeky 8 in there, we're good as gold, aren't we? So all of the numbers now balance. Balance the equation for combustion of butane. So we're burning it in oxygen. So we've got 4 carbons on the left. So now we have 4 carbons on the right because I put a balancing 4 in. In terms of hydrogen, so oxygen's on its own. This is something that happens quite often in a few of these questions. Oxygen's on its own, so we can balance it at the end. 10 hydrogens on the left. We've only got 2 on the right. So if we chuck a 5 in front as a balancing number, the carbons are sorted, the hydrogens are sorted. I've given us 8 oxygens plus these 5, so it's 13 oxygens. If you put 6.5 in here, times 2 will give us 13. Okay? So it's easy as that. The last one we'll do, balance the equation below. So 2 nitrogens. So the only way to possibly balance that would be to put a 2 here. And now we've got the nitrogens on its own, so we can put whatever we want in front of that, balance it. So 2 times the 3 hydrogens gives us 6 hydrogens on the right. So that means we'll need 3 hydrogens on the left. Times by 2 to give us 6. So hopefully that makes a bit of sense. You can ask your chemistry teacher if it doesn't,